Okay, so let's start our lecture today. So, yeah. So let's continue with this one. So, yeah. Let me pull out the text. Okay. So, let's see. So, okay. So, yeah. So we have showed this before. So, uh, so let's see. So, mm, okay. So, okay. So, since we have the sum of our let's use the n from 1 to infinity of 1 over okay, so omega n cubed is finite. Okay. The Y-stress M test. Y-stress M test gives uniform absolute convergence on compact subset avoiding the lattice. Uniform absolute convergence on compact subset avoiding the lattice. Subset avoiding the lattice. The lattice. Okay, so so okay. Yeah, I think the Y-stress M test. Okay, so we want to show that. Yeah, so we want to show that this guy converges uniformly on compact subset of U, right? So basically what we do is that we can so we can fix a radius, right? So let's say we fix so basically I think the question is that so we know that the okay, so I think the y-stress m test just gives the uniform absolute convergence of this function, right? Of these partial sums, right? So if we define the partial sums as like an Sn, right? So we defined it before, right? So let's say this. So let's recall the argument. So with that, S of capital N to be equal to the to be equal to the sum from 1 to n of this guy, right? Wait. Okay, I forgot the y-stress m test. So let me pull out the I think the y-stress m test is not about these S's. So let me see. So shoot, there is no internet. Okay. Okay, so the y-stress m test is not this one. Okay, it's not this sums. Okay, so it's about the each term. So we let this small fn to be one to be like each of the summand, right? And then we show that, so because for each of the summand there is upper bound, right? Of course for this n large, but for n small we can handle it by picking the supremum, right? Because there's only finite many term that is less than 2r. So the sum is finite for small, so for this small n, which is inside 2r, and for the large n, that is outside this radius 2r, we can control it by this term. So therefore, the absolute value of each of these fn is summable, which satisfies the condition for the y-stress m test. So yeah, so of course I think we need to pick with this r correspondingly, right? And fix this radius r to be fix r bigger than 0 such that wait, I think I need to be a little bit careful here because Okay. Yeah, I'm thinking of the issue where okay, never mind. Because I'm thinking of the issue where okay, never mind. Yeah, I'm thinking of the issue where there's some potential. Yeah, I don't think there's an issue here. Okay, so yeah, fix r bigger than 0 such that yeah. So maybe I'm thinking of the issue that such that let's see this. So the disk center at 0 of radius r closure contains the set U, right? Okay. Yeah. So there are some lattice point inside this because this is centered at 0 of radius r, right? So it's centered at 0 and then radius r. This U is just a neighborhood around this theta node, right? So here we have this centered at 0 of radius r. So basically, it may contain some lattice point, some other lattice point, right? So then so why do we have the so this may cause us some trouble maybe will it? So this is 0 and then the radius r basically is just some large radius that contains the closure basically is a closed disk. Okay, so here I'm not drawing here. Okay, so this is the closure, and then there are some maybe other lattice point inside. Okay, so but here this convergence is the compact subset avoiding the lattice, right? So okay, so I think I figured out how to avoid this. So okay, so here let's do a little bit manipulation here, because here, literally speaking, this zeta node it is a lattice point, right? So basically, but the thing is that here, our enumeration, our Fn, which avoids this zeta node, right? Right. So this enumeration avoids this zeta node. So basically, this zeta node is not a singular point corresponding to this sequence, relatively to this sequence of functions. So there's no trouble that we pick a compact subset. So why can't we pick a compact subset of this U? Yeah, of course we can pick a compact subset, right? Because just take a ball that contains this zeta node, and then the ball we can pick a compact subset of a ball, right? So let K be like K be a subset of U be compact, okay. And also we have zeta node is in K, right? Okay. So basically we fix the compact set. This K, okay. And then for this K, right? So M test. So we run the M test on this K, okay. So M test implies that okay, the infinite series n from 1 to infinity of this Fn, right? Z converges. So namely, because the two conditions of M test are satisfied, right? So one condition is that the Fn is absolutely bounded by, so for small m, so for small f, we can just bound it by the supremum taking over the compact subset of this K. And for upper one, we can also bound it by this guy for this n large, right? So there's no problems. So these two conditions for M test is satisfied here. So therefore we have that this Fnz converges absolutely and uniformly. Okay. On K. Okay. Okay. So okay. So now now what we do? So oh yeah. Yeah, so this is true, right? Okay, so therefore this guy, right, is holomorphic. Okay. Oh, there's a cat here. Okay. So therefore this guy is holomorphic. Okay. So therefore, okay. So let's say hi to the camera. So this is a cat here. Okay. So okay. So okay. So therefore, so the summation omega not equal to 0 and zeta naught of this term z minus omega plus 1 over omega plus z over omega square, okay? Okay. Wait. So let's see. So oh yeah. Converges. Okay. So converges locally uniformly. I think this is not only true for K, right? For this K, I think it is true. It is true for any complex subset avoiding the outer lattice, right? Yeah. Yeah. So not just this K. Okay. So yeah. So not just this K. Right. So because we can apply the same argument for other complex subset, just pick a bigger radius, and then apply the same argument here. Okay. Right. Okay. So okay. So converges locally uniformly. On any compact subset of this wedge. Wait, what happened? Okay, wedge minus 0 and this data now. Okay. So this is the lattice. Excluding 0 and data now. Okay. Okay. So yeah. Okay. So oops. Okay. So okay. So so therefore yeah, so therefore let's see. So yeah, so therefore we get a holomorphic limit, right? So therefore this function is holomorphic, right? So this is well defined and holomorphic because of the compact uniform convergence. Because the uniform convergence are compact subset of holomorphic functions, give you a holomorphic function. So therefore this is a so this is a holomorphic function. Yes, so this is a holomorphic function. Okay, so then let's see a name. What's the name? So let psi, okay, z be the holomorphic limit, okay. Okay, so this function is being defined on C. Whoa, wait. Okay, definitely not convex subset of this lattice point. Okay, this is C minus this lattice point. Okay, because this complex set needs to avoid this lattice. It don't need to avoid this data node. So lattice point other than lattice point other than data node. Okay, other than data node. So C take away this set. Yeah, so take away this set. Okay. So maybe I use this one, a bracket. C take away this set. Okay. So this is a holomorphic function. So this is, I'll just use the zeta cosine z, okay. And then, so this is a holomorphic function on shoot. Okay, so so this is a okay, so this function is being defined on 0, right? And also defined on zeta naught. And then this function is not defined on 0. This function is defined on everywhere. So, okay, but, okay, I see why I just use u here. Because here, in order for us to compute the Laurent series expansion, we only need a neighborhood u of this zeta naught. We don't need, but okay, but the assume is fine. Okay, yeah. So here, what we have is that, so this is definitely well defined on u, right? And this is well defined on u, and this is well defined on u. So yeah. So what do we have? So we have, so this is the singular part, right? And then this is a holomorphic. So this function is this function. Okay. So this is a non-singular part. Okay. So this function, let's use a letter to denote this function. So yeah, so we finished this one, right? Yeah, so we show this part. Yeah, so okay. So let's say that this capital F z, okay, so to be equal to 1 over zeta naught plus z over zeta naught square plus 1 over z plus z cosine z, okay. Okay. So fd fd is holomorphic. Holomorphic on u, okay. Oh, sorry, I erased what I defined u, but okay. So f is holomorphic on u, okay. So yeah, so the question is that okay, so I think there's a theorem for the Laurent series expansion about the coefficient. Yeah, so let's see. So okay, maybe I think I need to start here. So let's see that next time I'll try to compute the Laurent series expansion of this zeta z at I did not. Okay.